talk about how we scaled Pinterest's monitoring system. Specifically, I'm going to focus on how we scaled our time series monitoring system. I'm going to describe what Pinterest is, where we started from 4 years ago, the challenges we faced, what we missed, and some other lessons that we learned, and then I'll just wrap it up with a summary of 3 bullet points that I hope you take away from this 30-minute talk. So first, what is Pinterest? Well, Pinterest is the world's catalog of ideas. Users discover, save, and do these ideas in real life. An important thing is that Pinterest runs entirely in the AWS cloud. So let's start when Pinterest launched. Pinterest launched in 2010, but it didn't start gaining traction with users until 2011. It started taking off at the end of 2011, almost doubling between January 2012 and April 2012. So this is a good time to start our monitoring story in early 2012 when user growth is almost doubling. So in early 2012, Pinterest was not using many tools for monitoring. There was Ganglia, which we mainly used for system metrics like CPU, memory, disk, network usage. We used Pingdom to at least know if the site was up or down. But given the quickly growing number of users on the site and the increasing complexity of the stack, the lack of visibility started hurting uptime. Well, just how bad was uptime? Well, there were frequent outages. For example, in April of 2012, there were about 10 outages a day. However, in June, that number got better, but not for a good reason, mainly because the outages lasted much longer. It became clear during this time that we needed a better way to see what was going on within the stack. Luckily, there is an open source tool called Graphite that we heard made it easy to get started with time series metrics. So we decided to add that to our infrastructure. And here's a timeline, just to put this in perspective. Monitoring has a star next to it, just so we have the definition. And for background, Graphite was originally developed at Orbitz in 2006 and was later open sourced. This tool stores time series data and renders graphs of this data on demand. So in the beginning of 2012, we added this to our monitoring stack. Our first Graphite architecture consisted of application code sending metrics using the statsd protocol over UDP to a single box. This box ran on the statsd server to aggregate, or this box ran the statsd server, which aggregated the metrics, and then sent it to the Carbon cache to record the metrics to disk. The Graphite web interface also ran on this box, which served and rendered graphs to users. This architecture allowed us to start adding application metrics extremely quickly. We used the generic statsd client for Python. We were able to start logging calls by any engineer with a simple one line of code. Now, as we were adding metrics, we did not want a problem in the metric system to affect the site. So we used UDP to talk from the application to the statsd server. Now, this is where I would normally tell a UDP choke, but I'm afraid you might not get it. Now, the key thing here is that everything ran on a single box. A requirement of monitoring systems is that they need better uptime than the systems they are measuring. So even with a single box setup, we had about 8 hours to bring up a replacement and still meet this requirement. So we were golden. So believe it or not, this box lasted almost a year, even as the number of visitors to the site was growing. The key thing is the box scaled with the number of engineers, not the number of users to the site. More engineers equaled more metrics getting added to the system. More metrics means more disk usage, and then that's when the disk latency became the bottleneck. In Graphite, every metric is a file on disk. So more metrics means you get a Ganglia graph that looks like this. But luckily, fixing the disk latency had a simple solution. We just need to add more disks. So here's our second graphite architecture. In the second version, all components were split apart. The only part that looked the same was that the application still talked to a single statsd server. From the statsd server, a load balancer routed metrics to a carbon relay, which used consistent hashing to map a metric name to an individual backend graphite box. The graphite web interface still ran on each box, but then we had a load balancer to route user requests to a specific random box. Now, the second version of this architecture still did not address the downside of using UDP to talk to the statsd server, the packet loss problem. And here's a ganglia graph showing something not good. Those are all metrics. They could matter, they could not matter, but it's so many that it's going to hit something that matters. So it was clear that we needed to reduce the load on the statsd server. There are two ways to do this that were easy to implement. The first was to push the statsd server to all hosts. I call this statsd for everyone. Doing this required putting the host name as part of the metric name, since all the aggregation now happened on the host. If the host name was not in the metric name, Graphite would just take one of the metrics from a single host for a given time window for metrics with the same name. However, putting the host name in the metric took up a lot of space on the backend servers because each metric is a pre-allocated file. In addition, we used auto-scaling, which made this approach even worse since new hosts would have a different name. The more we auto-scaled, the more we ran out of disk space. Luckily, we have another option. The second approach was to shard the statsd server based on the metric name. This ensured all aggregation happened on the same statsd server for a given metric. The downside to having the shard mapping in the client was that all statsd clients needed to be at the same version. This is very important. If they were not at the same version, different statsd servers would get the same metric name, and only one would get recorded for a time window. Updating the statsd client in this way made it very difficult because there was no way to ensure that the version would remain the same as you did the update. Since the first solution didn't work, though, we chose this solution. However, before the solution could completely fall over, the backend became overloaded again. We had more engineers, and more services were being created. Some of them were even created in this language called Java. So we wanted to keep that separate from everything else. So we just made another cluster for the Java metrics. We could have added more boxes to the existing existing Graphite cluster, but adding more Graphite boxes is not as simple as just running an EC2 run command and then adding and running Graphite. So we just spun up a new cluster. Another benefit to having another cluster is if one cluster became overloaded, it did not affect the other cluster. But it did have a downside in that we had more maintenance, more clusters, more maintenance, more routing rules in the client of which cluster to go to. Plus, as the number of services increased, we cannot just keep adding more and more Graphite clusters. Now, so far in the scaling section of the talk, I've been focusing on the ability of the system to handle write traffic. But this is ignoring an equally important part of how the system is used. Here is a user quote from an email on actually getting the metrics out of Graphite. It is clear that even though we are able to handle writing this data, users are not able to query it. What's the point? Users are clearly wanting more cardinality out of their metrics. You could say that the user is using the system wrong, but the data the engineer was trying to gather seemed like a reasonable use case that we should support. Around this time, a new time series database based on HBase was gaining popularity, OpenTSDB. Since Pinterest already had HBase experts from the product side, we decided to install this new system in addition to the other systems we already had. So OpenTSDB is a horizontally scalable time series database built on top of HBase that we deployed in 2014. Notice that this was almost 2 years after we first installed Graphite. Here's a quote from that same user as before on getting the same data out of OpenTSDB. This user is much happier. This has to do with the design of OpenTSDB, of allowing metadata for metrics to be added as tags instead as part of the metric name. In fact, if it is a part of the metric name, it does not perform well either. OpenTSDB does not natively support globbing on metric names. Unique parts always should go in the tag values. At this point, we have OpenTSDB and Graphite for application monitoring. Ganglia is still there for system metrics, but how the metrics are getting to the backend system is still broken. We never really fixed this issue. We kind of just punted it off for a little bit. Now, earlier I mentioned, is that really affecting the users? Does this impact the graphs the user sees? Yes. This is causing the graphs to be just plain wrong. The drops that you see here are caused by losing packets. Even though these are operational metrics, these are the basis for alerting on this site and need to be somewhat accurate. So what do people think of this situation? Well, these quotes are pretty powerful, so I'm going to read one. At this point, I would give just about anything for a time series database that I could trust. The numbers coming out of Graphite from the client and server sides don't match, and neither of them match with the Ganglia numbers. So in the second quote, he's saying the shapes aren't even right. So it's not a good situation to be in. So we need to replace the statsd server. We did this by adding 3 new components. We have a local metrics agent to collect the data per host, which then sends it to Apache Kafka, which is a distributed message broker. From Kafka, Apache Storm will read the metric data, aggregate it, and then send it to Graphite and OpenTSDB. So let's look more at the metrics agent. The metrics agent becomes the gatekeeper for time series data. All writes into the system happen through the agent. Since all writes now happen through the agent, this agent has to support the statsd protocol and the OpenTSDB put statement format used by other tools. Another benefit to having our own agent is that this allowed us to change the tires while the car was being driven. The conversion from the existing pipeline to the new pipeline could happen without any negative impact to the metrics, the alerts, or even making it worse for the users. To do this transition, the application wrote to the metrics agent, which acted as a proxy to the existing statsd servers. Once all the clients were now going through the metrics agent, we could send the data to Kafka and stop sending the data to statsd. One problem with reading from Kafka, instead of getting the data pushed directly to an aggregator, the statsd server, is that at some point, you have to consider the data complete. So we decided, based on trial and error, about 30 seconds after the current time, we decide that whatever aggregation we have done, it's complete for the last 30 seconds, and we push that data to the back end. However, the great thing about having Kafka is that we could easily throw on another consumer with a larger window of, say, 2 minutes, 5 minutes, and then write an updated set of metric data to the back end. This has proven useful if a server gets rebooted or restored from backup. The batch job can replay data to catch the replacement server up. During the addition of Kafka, we also started doing double writes to duplicate Graphite and OpenTSDB clusters. At first, we did this to validate the conversion to the new pipeline, but it proved very useful to have a second cluster that was getting the same data written to it. For example, this allows failover if a primary cluster has an issue, or to perform maintenance such as compaction in HBase for OpenTSDB. So after all of this work, what do the graphs look like now? The data is finally correct in the graphs. How does this new pipeline scale? So right now, with this architecture, we're doing about 120,000 points per second in Graphite and 10 times that for OpenTSDB. At this point, we're trying not to add more metrics to Graphite, and we are replacing the high cardinality metrics in Graphite with OpenTSDB metrics. So far, we have focused on writing metrics, but I want to take a second to talk about how users read data from the system and interact with all of the clusters. In the beginning, after Graphite was added to our infrastructure, we decided to build a tool to unify all the other tools. We wanted to put all the time series data into a single pane of glass. This tool is called StatsBoard. StatsBoard performs time series dashboarding and alerting for Ganglia, Graphite, and OpenTSDB metrics. This tool handles the routing to different backends and which active cluster within the backend. In adding OpenTSDB support to this tool, we wanted to make the transition from Graphite easier for users. So we added many of the common Graphite functions, such as sum series, diff series, and a whole bunch more. Users create dashboards and alerts using YAML, yet another YAML config format. So dashboards, title, metric, alerts, threshold, and then PagerDuty, because everyone needs to get woken up at 3 a.m. While this hid a lot of details from the user, having StatsBoard abstract away the backend, this turned out to be a problem of its own. I want to talk more about the users of the system. User quotes on Graphite. It's nice that the tools are scaling, packet loss is fixed, and there's a unified interface for the tools, but just because the data is correct doesn't mean it can be interpreted. I want to read a couple of these quotes. I'm not saying Graphite isn't evil, it's evil. I'm just saying that if you spend a week staring at it hard enough, you can make some sense out of the madness. And then our response, of course, is, I do not believe Graphite is evil. This is how ROD data sets have worked since 1999. It's like, come on, get it together. This is how they work. But the last quote sums it up pretty well. The problem is that you need to know a lot of things to get correct results from the Graphite plot. And none of these things are easy to find out. So he's referring to like aggregation, intervals, summarizations, difference between stats counts, and how those get aggregated. And I'll go more into that in a minute. Now, just so Jason doesn't think I'm picking on his upcoming book and the book signing everyone's attending later today, what about OpenTSDB? I thought those users were happy. The quote from before made it seem like everything was great. Well, here's a quote from a user. Something is wrong with OpenTSDB. My lines are often unnaturally straight. Can you fix it? So unless you know the details, the behind-the-scenes details of these systems, they can be hard to interpret. So what we recently have done, and should have started a long time ago, is started a user education campaign for our time series tools. We started doing several things to educate the users. We started with hands-on labs, and then went with different levels of tutorials depending on how deep the audience wanted to go. For Graphite, we explained the concept of round-robin databases to users and how the system will perform when querying across time boundaries. We talk about how metrics get summarized to the next interval. For example, is the max of an interval taken or the average for a timer? This is important because people often look at historic data and need to understand how it's been summarized. Also, how do I get requests per second from a timer? The problem is you need to know the sample rate. Where does the sample rate live? In the code. But if the code's changed, well then, I don't know. You have to look at the Git history. How does the stats dot, a rate, get summarized differently than stats counts? How do I even know to ask this question? So that's what this user education campaign that we started did. So for OpenTSDB, we talk about rates. For example, when users first start using the system, they'll see that the CPU utilization metric just keeps on going up. That would be pretty impressive if that was actually the utilization. But sadly, it's a rate. But the users need to know what a rate is. We teach them interpolation of data points, what that means for your graphs, which aggregator to use to not get the interpolation. And a big one is like, what is aggregation actually doing? Slow queries? Help. I have 8 tags. Each tag has thousands of distinct values for every time point. The data comes in at 1-second intervals. Can you help me load my data for the past 6 months? No. So what else have we learned besides system architecture and doing user education? Well, we need to protect the system from the clients. Now that site availability is high, the availability of the monitoring system must be even higher. Architecting for high availability with multiple clusters, duplicated data, will not help if certain metrics start hammering the system. A high number of unique metrics can flood Kafka, cause Graphite to quickly run out of disk space, or HBase to have high call queue links, making both systems unavailable. Solving this was not possible until we made sure all metrics in the system came through something we control, the metrics agent. In this way, we could alert on what metrics were coming in and then dynamically update a metric blacklist that would go out to all machines. Next, if there's data in this system, we should also make sure it is correct. We cannot control what users do with the data. For example, not that this has ever happened, using operational metrics for business decisions when the expectation of the system might be that only 90% of the data gets stored. Well, the question is which 10% is missing? If we're going to trust the data, we need to monitor that it is accurate. So we count metrics generated and sent at each step in the pipeline, and we alert on discrepancies. The problem is there's still a lot of missing pieces, a lot of places metrics can get lost, and that we don't know that it's lost. So we're continually adding more data on the system. Another important thing is how aggregation happens. Even with statsd on the local box running inside the metrics agent, it is still using UDP over the loopback interface to send data. If enough metrics are sent at once, data can still be lost. There's a different model in the Java world where metrics are collected in the same process and then they can be queried dynamically from a given port. This makes it extremely efficient to update metrics. For example, if I want to update a counter, I just do an increment call. It all happens within the same process. In statsd, I context switch the kernel, context switch back to whatever app is receiving it, and then the process repeats. So that's not very efficient. However, the problem with the Java approach is that all of the metrics get aggregated inside of a single machine. Getting cluster level percentile data, which is what the user actually sees, is not possible unless we can get the raw histogram data from each machine to be summed up by Storm later. The other problem with the first approach with statsd is that users should never have to ever tune the sample rate. Service requests per second change over time, and it should not be the user's job to make sure that the sending metrics is a problem. We want the barrier to entry to send metrics to be extremely low. This is very important. We want to lessen operational overhead. We want to reduce it, but it's not always possible. We keep adding tools. We never get rid of anything. Each system has its own unique quirks and overhead to run. The more systems we have, the more work it is to monitor those monitoring systems. So at this point, some of you might be thinking, hey, you have all these time series databases. Maybe you could just remove Graphite in favor of OpenTSDB. Sorry, Jason. This has its own problems. OpenTSDB does not do summarizations. all points are stored as they are sent indefinitely. However, graphite does. These summarizations make loading historic data fast. Another reason that we cannot get rid of graphite is that a lot of graphite metric names have semi-unique fields which require globbing, but OpenTSDB is not optimized for this use case. These need to be put into the tags instead. Metrics have to be examined individually to identify the optimal OpenTSDB format to use. There's not a ton of immediate payoff to do this. However, we are focusing on the highest cardinality use cases, since these are almost impossible to read from graphite anyway, and they're also taking up valuable space in the system. Reducing operational overhead is not always compatible with choosing the best tool for the job. For example, users really like how Ganglia displays system metrics. However, we have the same metric or the same data in OpenTSDB. We can reduce overhead by getting rid of Ganglia, even though some users consider it a superior tool. So retiring tools is hard. In Corey Watson's talk yesterday, it sounds like they started from scratch at Stripe. I'm pretty jealous. If we did the same thing, this would reduce operational overhead and make user education much simpler. Another important piece that we missed is setting user expectations on what the system can and can't do. Users assume many things based on the tools that they already know. For example, users expect their email provider to not delete their data. These tools do. These are not magical business intelligence tools that run complex queries and return data instantly. Another common problem is that users need to have an expectation of how difficult it will be for a metric to be queried. For example, writing a metric with the host metadata and several other tags and only querying on the aggregate of all the hosts does not make sense. We have to set these expectations. Once we set the expectations, users are much happier. So, in summary, we have had to match the monitoring system for where the company is at. Graphite worked as the only application time series tool for almost 2 years. It did not make sense for us to build and optimize the OpenTSDB cluster with double writes and failover if the databases that actually contain the user data were not getting backed up. Also, adding a bunch of infrastructure that only monitoring tools would use, things like Kafka, Zookeeper, Storm, is time-consuming. This was much easier after other teams in the company started supporting these tools. A very important thing is that user education on these tools is extremely important. We're now doing labs, tutorials, office hours to make sure that these tools scale across the organization as the number of engineers grow. Thank you.